Okay, so moving on over to the aprint procedure in the format package. So how does this differ from the regular print procedure and what do we use it for? So in the previous videos, we saw that the print procedure is something we use to send data into the standard output, and then typically speaking, that data will be printed out to the terminal window. Or if we want to, we can redirect the standard output to then save to a file if we want to preserve what we're putting inside of it for later viewing, because obviously when we close down our terminals or consoles, we lose all that information. It's not consistent. And that really works well for the standard error as well, for redirecting those outputs. Now, the aprint, however, is not actually for printing out output to the screen immediately. What it is for building strings. And you can see here that it returns a string. And when I say building strings, I mean that quite literally. If we look over here, we can see in the format.odin file, which is inside of the core directory, we can see the actual implementation of aprint right here. And we can see that it returns a string, but if we look inside of the body, it's literally creating a string builder and then just calling SB print underneath it. So it creates an object stir of type string builder. It sets up, it initializes the string builder with an allocator, and then uses the SB print function to actually get what we want. So realistically speaking, what we could do is ignore aprint altogether and just use the string builder. However, you can see that if we just want to create a simple string right away, aprint kind of abstracts a few lines of code away from us, so we don't have to write these 3 lines of code each time. That was one of the benefits of aprint, rather than having to build a string each time. And like I said, we need an allocator for this. So if we go back to the documentation over here, we say one of the parameters that is a part of this procedure is the context.allocator by default, but it requires an allocator. This is what the A in aprint stands for. It stands for allocated print, because the string that gets returned to us is not created on the stack, it is placed on the heap. There is a procedure inside of here called bprint. If I scroll down and mash up bprint, if you wanted your string to exist on the stack, you could use bprint and supply the buffer yourself, but that's not what aprint does. Aprint is when we want the string that we are making to be dynamically allocated to the heap. So for that reason, you need to have an allocator attached to it. By default, this procedure just uses context.allocator. And to see this working, I've created just a little demonstration. So up top, we have a string right here, just to prove that it does in fact return a string. I make a object of type string, and then I call the aprint function. I just pass in a random string, and then we'll be printing that out. As we mentioned before, because the string is allocated on the heap, if this is a larger program, you do then need to go into memory management. You need to be deleting these strings when you're done with them, or else you're going to have a memory leak in your program and you're going to run into issues later on. In examples like this, because the program is so small, by the time it gets to the final closing bracket, the operating system itself will see that this process has finished. The program is done, and it will just free all the memory up completely. So if you're only making small programs like this, you realistically speaking, you don't need to manually delete any memory that you've allocated. Although you could argue it's just a good coding habit to get into practice. If you allocate something, then delete it, which is where Odin's defer comes in really handy. And we can see down here, I've used all of the different variations of aprint. We have the regular aprint, we have the new line aprint and the formatted aprint, and then we have the aprints formatted new lines, just like the regular print functions we had and just like the eprint functions we had. They work identical to each other. They can take in just a simple string of text, or we can have some type of variable list of arguments to pass on, which can be from different data types. And if we were wanting to, again, I use this example a lot, creating a comma separated value inside of the regular aprint function, not the formatted print ones, we can change out the separator value to be a comma. Instead of all these items being separated by a space, they are separated by a comma. Then going down, we can append a new line to the string. So the end of this string here will have a new line appended to it. Of course, you could get the same effect by just typing in the \n character. Up to you how you want to do that one, really, but that is an option. And then finally, we have the formatted print version of aprint. So we just take in some string, and instead of passing the values in separately like this, one by one, we can then choose where these values and how they are interpreted actually show up in the string. So here I'm printing out the variable x right now, 1, 2, 3, print its value out, what type x is, and what the actual bit pattern of x would be. And I think this here is the main way that I personally would use aprint. When you have some type of other data type other than a string that you want to combine together, it's quite common in programming. You might have an integer or float or bool, and you want to add that into a string, and then you want to use that data somewhere else but as text. This is a very quick and convenient way of creating a string like that. You can see by just passing in the placeholder values that I get a string that has the integer value, the actual type of it, and the bit pattern if you ever wanted to see that. And again, finally, we have the new line version of formatted new line. Essentially get the exact same thing, but it is as if I appended a new line just like above, as if there was a backslash n on it. As we mentioned before, because these strings are allocated on the heap, and if this was a larger program, what you would need to do is delete them to manage your memory properly. So up here, you can see I delete string 1 right after we finish with it. But down here, I try to then print out string 1 to see what will happen. Will the program crash? Will the operating system go, no, you've deleted that memory, don't touch it, don't try to go there? Or will something else happen? You can also see here that I use the defer keyword. What this means is defer states that when you leave the current scope that you were in, so when you leave the current set of curly brackets that you were in, execute the code that I have. So in this case, once we reach this final line of code, so when we're printing out string 1 again, we are going to leave the final curly brace of this whole program, which the defer is currently contained in, and then we will print out the line that we are manually deleting, manually calling delete for string 2 in this case. And we delete string 2. So we're going to run this program and then see what happens. And for the most part, you can see it works kind of as expected. We have just the regular string. We have the one that is separated by where all the all the arguments that we passed into it are converted into a string, but they're separated by a space. We have the one underneath where we change the separator value to a comma. So instead of a space, each individual argument that we passed in is separated by a comma. We then have the one that was printing in a new line. If you looked at the code, I didn't have a print new line statement above it, so the new line is appended. Then we have the formatted version of the print. Again, just a regular formatted string, but it makes it for a really convenient way of just turning integers, floats, bools, other data types into a string. And the same thing as above, I messed around with the values of x. That's another reason why this formatted print really works. If you have a variable, you can easily convert that variable into a string as it moves through its own sort of life cycle throughout your program, so you can constantly get values of them. And again, it appends a new line to that because it was the new line version. However, if we look below, we are reprinting string 1, and we saw that I deleted it at the very top. So by reprinting string 1, you might expect some type of error or something different to happen because it's being deleted. And it does. It looks like it's trying to actually print out the second string that we had. And this is because of the way the memory allocation has worked. So if we go over to here, we can see that a string is essentially down here, just a raw string once it starts getting used. And that is a pointer to an array of bytes and some length. That is essentially what a string is under the hood. It is this thing down here, a raw string. And in case you're wondering, if you just go up a little bit when you're inside of this file, which is the core.odin file, you can also see what context is. And you can also see where allocator is, and you can adjust this throughout your program if you want to. And just above that, you can see when we're using strings throughout our program, something called transmute is called, which is essentially taking all of the bits from one type and just copying them over into another type. So in this case, the string that we get passed, the strings that we pass into this string equals procedure, all just get transmuted into a raw string. Sorry, the data of this string. It won't actually be the text itself because we will be getting the pointer and the length. So this raw string essentially becomes a string, and that allows us to access the things inside of the structs there. So if we close these down, You see what's happening essentially when we first print out string 1 and we allocate the memory, some memory either on the stack or the heap, depending on how you're creating your string, will be allocated, and then the information from that string will be stored inside of it. The string itself will then have a pointer to the first byte of that array, and then it also has some length attached to it. That's one of the benefits of using Odin over C, because it's a more up-to-date modern programming language and it assumes you're using modern hardware, unlike C. We decide that it is beneficial to use the extra data to actually store the length of the string rather than having to go all the way through the string trying to find a null terminator character. If you're working on older hardware or embedded systems where you don't have much memory, that could be seen as a bad thing. You might think that storing the length simply costs too much memory. We can't do that. But in Odin's case, perfectly fine. It's how it works. So string 1 has the start of this array, and it also has the length of the array. So it knows how far to go and where to look to start reading. But what we did is we deleted it. Yeah, we deleted it. We deleted the memory there. And what that means, it's not like we just took a chunk of RAM and exploded it. It is still there. It is still a thing. The string is still pointing there, and it still has a length there. But the operating system is essentially being told, hey, we can start rewriting over this data. So when we create the second string, we allocate it again, and the allocator, I don't know how it actually works under the hood or how it's really implemented. I've not looked into that. But essentially what it has done is it's saying, well, string 1 was there, and we've just freed that memory up, so that memory is fair game to use. And it basically just pastes string 2 right above it. String 2 is longer than string 1 in our example, which you can see over here. String 2 clearly goes on for a lot longer. But string 1 still points to a valid array of bytes, and it still has no length that it can read from. And if we look in this example, down here we print out to hello world CA. And if we look at string 1, 1 makes string, it ends right at this CA. So that is kind of what has happened when we've deleted string 1. We've just told the program, the operating system, hey, this memory is free. You can do whatever you want with it again, read and write over the top of it. That's perfectly fine. String 1 isn't using it. However, string 1 still exists, and it still has its length, and it's pointed to the start of the array. Therefore, we can access that data again. Now, it could be if we did some other stuff in between. I've not tested this out yet, but because the allocator is essentially just copy and pasting over the top at that moment, I think if we were to do something like a for loop, so for I in, let's do 0 to around about 100, and then have it print out a load of stuff. So fmt dot print line, and then this can just be garbage text. It's just an example. If we save out of this and then run the program again, I've always spelled that wrong. I always miss the T off. I don't know why. It's a bad habit. So if we try this again, and this prints out, no, looks like the allocator still points to that bit of memory. I was trying to see if I had the programs do a lot of random stuff, maybe the allocator would start pointing to a different place, but that's obviously not quite the way it works. Anyways, that was just an example. That was a test. It's how you learn. Yeah, that was my overview talk, trying to explain how the aprint function works. Again, like in the other videos, if you have found out something that I've said wrong in them, I'm making these for my own learning, so feel free to correct me in the comments below, and I'll see you later.